Hey guys, we're going to go through 20.A, which is rates of change. And you're probably familiar with a couple of rates. Rates are just anytime you're comparing two different quantities. So two that you're probably most familiar with would be things like kilometers per hour or dollars per hour. So speed on the left, kilometers per hour when you're driving on the highway, or dollars per hour if you're working a part-time job, you might be making dollars per hour. Now, anytime we're comparing two rates, anytime we're comparing two items, it's called a rate, two different measurements. So over here, it shows you how the book is going to outline a couple of measurements. So when we see speed, the speed at which a car is traveling is kilometers per hour, and it's written like that with the -1 on the H. The -1 just means that it's on the bottom of the fraction, so that's just a similar way of writing km over H. Or ms, meters per second, will be m over s. The -1 just says that it's on the bottom of a fraction. So it's the same idea, it's just how our book's going to outline it. So when you see that notation, we know what it means. Fuel efficiency of a car can be kilometers per liter or liters per 100 kilometers, if we decide that. Scoring rate of a basketball player would be points per game, so like P over G, or we could see it written as PG with a -1, just to show that's on the bottom. Both of those are points per game. So down below it goes through ways that we can show rates for two people, their typing rate and the errors that they create while they're typing them. So Joseph typed 213 words in 3 minutes and made 6 errors, and Marie typed 260 words in 4 minutes and made 7 errors. Compare the performance rates of each. So because they're not typing for the same amount, the only amount of time, the only way we can compare them is by putting in the same unit, so per minute. So Joseph's typing rate was 213 words per minute per 3 minutes. So when we divide those, we got 71 for 1 minute. So when we're dividing, we're just finding out what it is for 1 minute. Joseph's error rate was 6 errors when he typed 213 words. So we got a rate for errors per word. So just almost a 3% chance he'll make an error on any given word, but that's how we get our error rates per word. Marie typed for 4 minutes and she did 260 words. So when I divide that, 65 words for 1 minute. And 7 errors for 260 words. That's really 0.02 errors per 1 word. So very small. Joseph typed faster rate, 71 words compared to 65. But Marie typed with greater accuracy because her errors per word was less than Joseph's. So we're going to look at a couple of examples here. First things first is Carson's pulse rate was measured at 67 beats per minute. So 67 beats for 1 minute. That's already a rate. It's a unit rate. Then it says explain what is exactly meant by rates. So this means that we're comparing beats to minutes. How many heartbeats would Carson expect to have each hour? Well, this gives us for 1 minute, but 1 hour is 60 minutes, so I'd have to multiply that by 60 to get 60 minutes on the bottom. Well, whatever I do to the bottom, I'll have to do to the top as well. So I'd take out my calculator and I'd multiply 67 multiplied by 60 to find out how many heartbeats we'd have for 60 minutes, and we had 4,020. So 4,020 beats per hour in this case. And that's what we have for the first one. So we'll continue down to the second one, and you'll see really similar. Let me just take this. Oops. So this one says, Janet typed a 14-page document and made 8 errors. If an average page of typing has 380 words, find her error rate in errors per word. So that's what we want to compare. I want to compare how many errors per word. Well, the information that we got so far tells us that she made 8 errors. And it told us that she typed 14 pages, and on each page had 380 words. So we'd have to have 14 times 380. So when I put that into my calculator, I'm still going to have 8 on top because there's 8 words for how many, or 8 errors for how many words do we have in the entire document. We're going to have to multiply 14 times 380. Oops, 14 times 380. And we get 5,320. So she made 8 errors in 5,320 words, but I want to know what it is per word, because the question says errors per word. So we multiply those ones, or divide those ones, 5320, and we get a number like 0.0015 errors per word. Whoops. So that's how many errors for one word. So very low rate. But then the next question says errors per 100 words. Well, if I know my rate for one word, I'm going to take these and multiply by 100 because that'll give me how many errors we'd have for 100 words. So when I multiply those together, we get 0.15 errors for 100 words. And that's the second one. So really similar, all we're doing is comparing two different units, and we put it in terms of one unit. So we'll continue down. Oops, doesn't want to go. Next one. Nico worked 12 hours for $148.20 for that week or whatever long. Whereas Marita worked 13 hours for $157.95, who worked for a better rate of pay. So when we're dealing with rate of pay, we're going to compare dollars per hour. So on this side, we'll start with Nico, and over here we'll have Marita. So I want to compare both those ones and see who makes more money per hour. Well, Nico, it tells us that he made $148.20 over a course of 12 hours he worked that week. Marita said she earned $157.95 for 13 hours. So we have our units in the same way. When I divide these ones, it's going to give me dollars per hour because the denominator will always become 1. So what I'm going to do is I'm going to take those numbers and we divide them together. $148.20 divided by 12 hours. It tells me that Nico made $12.35 per hour. And Marita will do the same thing, $157.95 divided by 13 hours. She makes $12.15 per hour. So, who worked for the better hourly pay? Nico worked for the better hourly pay. He made 20 cents more per hour based on their pay for that week. And we'll continue down. Clear my blackboard here. All right, so next one says, new tires, T-Y-R-E-S, have a tread depth of 8 millimeters. After driving for 32,178 kilometers, the tread depth on Joanne's tires was reduced to 2.3 millimeters. What was the wearing rate of the tires in millimeters per kilometers traveled? So it's giving us our rate that we want to compare. I want to compare millimeters per kilometer. So that'd be millimeters that has been reduced. So we know that this person's tires started at 8 and we were left with 2.3. So how much has been reduced? When I subtract those ones together, we get 5.7. We used 5.7 millimeters of wear on her car. Next it says she drove 32,178. So that's our rate that we're dealing with. So when I divide these ones together, that's going to give me the rate in millimeters of wear per kilometer. So when I divide these ones together, it's going to be a small number. 32,178. We get 0.000177 millimeters for each kilometer. So a very small amount of items, a very small amount of wear per kilometer. Next it says we want to know what it is in kilometers, 10,000 kilometers. So I'm going to write this number out again. And I want to know what it is, so I'm going to take each of these numbers and multiply them by 10,000. And when I do that, we'll get 0.177, oh, nope, 10,000, not 1,000. 1.77 millimeters per 10,000 kilometers. So that's the wear rate of the tires that Joanne's using. And we'll continue along to the next one. Alright, so next one says, we left Kuala Lumpur at 11:43 a.m. and traveled to Penang, a distance of 350 kilometers. We arrived there at 3:39 p.m. What was our average speed in kilometers per hour? So what we're going to do in this case is we're going to calculate the time. One thing that we do know for sure is 350 kilometers. That's the distance that we traveled. The time is the one that causes a little bit of trouble. So what we want to do is find out how many hours it took us to go from 11:43 a.m. to 3:39 p.m. Well, one thing that you could do, a good idea, is to use military time for this. So we want to see how long it took us to go from 11:43 to 15:39. So we've talked about this before, how we do that. Usually what we did was we went to the nearest hour. So I'll show you just a quick view here. So in this case, if I added 17 minutes, that would take me to 12 o'clock. Whoops. So that's going from 11:34. If I add 17 minutes at 12 o'clock, and then if I add 3 hours, that will take me to 15 or 3 o'clock. And then I have to add 39 minutes. That will take me to 15:39. So if I add up all this time, we end up with 3 hours and 56 minutes. So I'm going to write that at the top, 3 hours, 56 minutes. So what we're going to do, I'm going to take off this stuff down at the bottom here, now that we calculated our time. Is, well, 3 hours and 56 minutes is not 3.56. So if I want to put this in terms of hours, what I need to do is I would need to find out what is 56 minutes in terms of hours. So if I was to do this, I would say, well, 56 divided by 60 will give me the decimal. How many, or what decimal is 56 minutes of 60 minutes of a full hour. In this case, it's 0.93. So that means it took 3.93 hours in order to get to our destination. So I'm going to use that 3.93 because I just converted those minutes into hours and added it to the 3. So 3.93. So if I want to know what it is in kilometers per hour, all I need to do is divide these ones together. 350 divided by 3.93. We would get our speed of 89 kilometers, maybe 89.1 kilometers per hour. 89.06 it works out to be, but 89.1 kilometers per hour. So how about if we wanted to do this in meters per second? That's part B. Well, all I would need to do is take my kilometers and convert it to meters. And we know that we can do that by multiplying it by 1,000. So that would be 89100. Then I would have to take my hours and convert it to seconds. And I know that there are 3,600 seconds. And then it says, well, what is it in meters per second? So I would need to divide these numbers together to get what it is for 1 second, because it's nice that we have it in 3,600 seconds. And when I divide them together, we get 24.75 meters per second. Alright guys, the second part of this first section deals with average rate of change. So basically what it's saying is that in grade 9 we learned that if we had a straight line on our grid, that meant that the rate of change, or the slope, was always the same. And it says that. If the graph which compares two quantities is a straight line, there's a constant rate of change in one quantity with respect to the other. This constant rate is the gradient. That's just another word for slope of the straight line. If the graph is a curve, we can find the average rate of change between 2 points by finding the slope, or gradient, of a chord. That's just a straight line between the 2 points that I'm trying to find the average rate of change between. The average rate of change will vary depending on the 2 points chosen, so it makes sense to talk about the average rate of change over a particular interval. So if we look at this graph that we have down here, the average rate of change is always changing. So I see that we have kind of a straight line here, another straight line here, another straight line here, another straight line here. And you notice that they're not all on the same straight line, so that means that the slope is changing for all of them. So what we want to do is choose 2 of these points and find out the average rate of change, and that's what it has here. It says the number of mice in a colony was recorded on a weekly basis. Estimate the average rate of change, or average rate of increase in the population for the period from 3 weeks to 6 weeks. So what we do is we're looking at this dot here, and we're looking at this dot here, and we want to see what's the average rate of change. So that just says what is the slope between those 2 lines. It may not go along your curve, but we're just trying to find out the slope of those 2 points. So what we do is we just find the coordinates of those 2 points. So this one here, whoops. So this one here is at 3 and 100. This one over here is at 6 and looks to be about maybe, what did the question pick, 240. And then all we do is we find our slope between those. We use that slope formula, y2 minus y1 over x2 minus x1, and you can see that that's what's been carried out down here. We have our y2 minus y1 all over x2 minus x1, right? Just using our slope formula that we know that we learned back in grade 10. Same idea, so the next one, so part 2 says find out the slope over the 7-week period. So it's the same idea, different slope that we're working with because different starting points. We're starting from here and we're ending here, and we're looking for the slope of the line like so. So I would take the points 0 and 50 and the points 7 and what is that, about 310 or so, and find the slope between those ones. 315 they chose for that point. But that's the idea behind our average rate of change, is choose the 2 points on the grid and find out what is the straight line graph between those. So let's have a look at some examples that we have here. So 20A.2, for the travel graph given alongside, so the graph we have over there on the right, estimate the average speed in the first 4 seconds. So if we look at the first 4 seconds for this graph, I see that it starts here. 4 seconds are about here. So if I had to choose our points, I would look at this one as maybe being 0 and 2. And this one as being 4 and I would say about, let's say 2.4. And I want to find out what is the average rate of change over that. So if I was to do that, I would just take my y values and subtract them, because remember, y2 minus y1 over x2 minus x1. That's our gradient or slope formula. Oops, y2. Oops, what did I do? So y2 minus y1 over x2 minus x1. So I put these into our formulas. Doesn't matter which one you call y2. Maybe I'll call this point here 2 and this point here 1. Doesn't matter, you get the same answer at the end anyway. But we'll get 2.4 minus 2 all over 4 minus 0. So I get 0.4 over 4. And when I divide that, 0.16. So that means the average speed in this case was 0.16 in the first 4 seconds. And if we look at what we have here, it's meters in seconds, so it's meters per second. Next it says, how about in the last 4 seconds? So same idea, we're going to choose our spots on our graph. It's going to be a different color here. So we said this one here we thought was at 4 and 2.4. The last 4 seconds we have 8 and 6. And I'm just use the slope formula on that. Doesn't matter which one I call 0.1 or 0.2, just as long as we're consistent. So for this one, we'll subtract my y's. So 6 take away 2.4. Then subtract my time, 8 take away 4. And when I subtract those ones together, I see that we get 3.6 divided by 4, which is 0.9 meters per second. So you'll probably see that if I look at or compare these two together, you might see that the line that was created there was a lot more steep than the line that we had created between 0 to 4. And that shows that it should have a higher rate of change, a higher speed for that. Last one says, how about for the entire 8-second interval? So finally, that one would be a line that would just be from the start to the end. So from here to here. So if I look at that blue line, it's steeper than the yellow line, which tells me that's going to be a higher rate of change than 0.16. And it's not as steep as the orange line, which tells me it's going to be a slope that is less than 0.9. So I'll do that one up at the top here maybe. But the points that we have are 0 and 2. And 8 and 6, we already have that one on there. So when I'm subtracting them, we'll have 6 take away 2 for my y values, and 8 take away 0 for my x values. We get 4 over 8, which is 0.5. So 0.5 meters per second is the average rate of change over that span of the beginning, 0 to 8 seconds for that one. Alright, so we got our last one here. This one talks about the amount of poison that's used on grass. As the grams of poison that we use on grass increases, the number of beetles that are found in the grass decreases as you read that graph from left to right. So the rate of change is negative in this case because the beetles are decreasing. So it says estimate the rate of the beetle decrease when the dose increases from 0 to 10. So on our graph we're looking at a spot here, which looks to me to be about 0 and 35. and 10, which looks to me to be about 10 and we'll say 2. So what I'm going to do is find my slope, my rate of change between these. So when I subtract my y's, 2 take away 35, divide that by 10 take away 0, we'll end up with negative 33 over 10, which is negative 3.3 beetles per gram. So for every gram that the poison increases, we lose 3.3 beetles in the grass because they're no longer there anymore. So that's the first part. Second one says, what about between 4 and 8? So we go back to this graph, same idea. I'm going to take off the ones that we know. So we're just looking at the average rate of change between different spots. So 4 would be about here. I'll use a different color. 4 would be about here, which is 4 and 25. 8 would be about here, which looks to be about maybe 8 and 8. And we find the rate of change between those. Doesn't matter which point we call point 1 and point 2, we subtract our y's. 8 take away 25. On the bottom we have 8 take away 4. And when we do that, we get negative 17 over 4. And when I divide negative 17 over 4, we get negative 4.25 beetles per gram. So the rate of change is a lot more. So if I imagine the graph that we have up here, it's a lot more steep than the graph would be between 0 and 10. Something like that. So you see that that blue line is more steep, a little bit, not a whole lot, but more steep than the orange line that we have up there for our different rates of change. Finally, last one says, describe the effect on the rate of beetle decline as dose goes from 0 to 14. So I'm going to take this off. So this one's for describing. What we might see is that it decreases, use a different color, it decreases, goes faster in this section, so it's between 4 and 6 it's decreasing at a faster rate. However, once we get to about 10, it flattens out. So using more than 10 grams of poison doesn't have much of an impact on the amount of beetles because it flattens out quite a bit over that section. So we can describe that's what happens. You can also find the average rate of change if you wanted to between the start, which looks to be, as we said, 0 and 35, and the end, which looks to be about 14 and 2 or so, and find the rate of change. You can discuss that as well when you subtract them, but just describe